Last lecture, we looked at the idea of a tree in general. We looked at an implementation of a tree, and that tree we looked at had the possibility of having many different children. Each node could have an entire array list of nodes. There is a subset of the tree data structure which constrains that child structure even more. And that subset is called a binary tree. A binary tree is called binary because it can only have two possible children. And we talk about the children in terms of a left child and a right child, or a left node and a right node. A binary tree is a special case of the general tree structure, and it sort of boils down to the bare minimum what makes something different between a linked list and a tree. Well, it's that having one additional follow-on node besides a linked list. So instead of having a next, we have a left and a right, splitting our descendants into just two different subtrees. Let's look at maybe two or three different ways in which we can use binary trees. One possible way in which we could use a binary tree as an application, if we had one available to us, was as a decision tree. Now, decision trees are often used in environments like maybe diagnosis of mechanical problems in complicated machinery, like maybe a helicopter, or diagnosing the faults in a car. It can be used just in your own personal life, trying to make a decision between things you care about. It is also used in the game of 20 questions, a decision tree. And so all of these are different ways in which we can structure decision-making process, or diagnosing a disease is another one. We can structure a decision-making process as a binary tree. And the data that we'll keep at each node of our binary tree is a question, and we're going to follow down the left and right nodes of our tree based on whether the answer to the question at that node is yes or no. If it's yes, we'll go one direction. If it's no, we'll go the other direction, and we'll run into another question. We'll see if that question is yes or no, and we'll keep walking down our tree, taking left and right branches until we get to a leaf. And at the leaf, instead of having a question for data, it has a decision for the data. So maybe if you're playing the game 20 questions, it is the thing you were thinking of. If you are diagnosing a disease, it is the most likely disease that you've got. Something along those lines. So, for example, here's an example of how we might use it in animal guessing games. The first question, the root of our tree, we might have a string, which was the question, is it a mammal? And based on whether the user says yes or no, we might say yes, and we'll go down the yes branch. Then we'll ask the question at that node, does it have stripes? And if the answer is no, we'll go down the no branch, and we'll guess that it's a pig, because a pig is a mammal that does not have stripes. And so as we follow the path from the root all the way down to the leaf, we arrive at a decision at our leaf. Now, if it's the case that we have arrived at a leaf, and the thing that the person you're playing with, if they weren't thinking of a pig, let's see, what's a mammal that doesn't have stripes? Maybe we'll say like a hamster. So we would have to add some kind of an additional question at the bottom of that leaf in order to differentiate between a hamster and a pig. Like maybe we would say, does it live on a farm? And then we would add another node where it as a pig is, and those two nodes would have a leaf as well. So we can build up our decision tree game by expanding this tree as we go along. A more technical way in which we can apply a binary tree is in something called a Huffman tree. A Huffman tree is a way of doing compression, of doing lossless compression, meaning we're going to compress a file without losing any data. And the way we're going to compress the file is by, let's talk about it in terms of a text file. And we'll talk about wanting to represent the characters in that text with ones and zeros like we already do, but we're not going to use the same length of ones and zeros. So in a typical UTF-8 representation of a text file, each character takes either 8 or 16 bits in order to represent it. In a Huffman tree, we can use a variable number of characters to represent that letter. And what we're going to do is we're going to assign shorter codes to more frequent letters and longer codes to less frequent letters. And in that way, we're able to compress the size of our overall file by using very small sequences of bits in order to represent rare letters and longer to represent, long sequences of bits for rare characters and short sequences for frequent characters. So what the Huffman tree does is it gives us an algorithm for doing the compression. The leaves are going to contain the character that we want to encode, and the path from the root to the leaf is how we encode that particular character. We'll walk along the path from the root to the leaf, and we will use a 0 or a 1 depending on whether we turn left or right in order to construct that tree. So let's look at a tree that's built on the Hawaiian alphabet. The Hawaiian alphabet uses a subset of the letters in the full English alphabet. And so, for example, in this case, if we wanted to encode the word aloha, A-L-O-H-A, what we would do is we would walk down the tree, representing the A as a 1, 0, and L as a 0, 0, 0, 0, the letter O as 0, 0, 1, H would be 0, 0, 0, 1, and then A would be 1, 0 again. The building of this tree is a task for another lecture. We won't talk about that today. But what you can see embedded in this tree is the assumption that an A is a very frequent character, but for example, a W and a P are very rare characters. This is called a Huffman tree. You can use it for both encoding and decoding, whether you decide you're going to produce the ones and zeros or consume the ones and zeros. Finally, a third example of a binary tree is an expression tree. We saw trees used in a way in order to evaluate expressions when we made recursive calls looking at ways in which to actually evaluate a tree. But we can actually represent the tree itself, represent the equation itself, the expression itself as a tree, where each interior node of our expression has an operator, and the left and right branch each hold the operands of that operator. And then we can have recursively defined trees as well. So if we look at the expression parenthesis 3 plus 4 paren times 5, we can represent that by the tree on the left, where the first operation we do is 3 plus 4. That gets evaluated, and the result of that expression gets multiplied times 5. The same characters, but without the parentheses, would be represented by the tree on the right, where first we do 4 times 5, and then we add it to 3. The expression on the left gives us 7 times 5, which is 35, and the expression on the right gives us 3 plus 20, which is 23. So this expression tree uses a binary tree, because the assumption is all of our operators are binary operators, but enables us to represent the different orders of operations that are encoded with parentheses or without parentheses as well. When we have binary trees, one property that we like to have of the binary trees is we like them to be balanced. And by balanced, I mean that each of the subtrees going down the left and right side has approximately the same number of nodes. This property of having a balanced tree, ensures that any divide and conquer algorithms that we want to do in the future maximize our efficiency. We'd like things to be log n rather than order n, and a balanced tree helps us to do that. Because you can imagine that a binary tree, if things were only children of left nodes, would degenerate into a linked list. And so we want to keep things balanced in order to get the benefit of the balanced tree. Here's an example of two trees. The red one is balanced and the blue-green one is not. That is because the blue-green one has very radically different heights on the left child and the right child. But the red tree, at every node, the left and right child are all only differ by at most 1 in their height. And you can see that that property is preserved even as you recursively descend the tree. There's no node you can find where the left and right side has a height that differs by more than 1. And that's a definition of a balanced tree. When we do this, we can reason about the size of our tree. Because of the way that the tree splits, we can identify some different formulas for a tree. For example, we can identify that a binary tree that has a height of h can have at most 2 to the h minus 1 nodes. And if you think about that, we look at a completely filled binary tree that has a height of 4, it splits at each particular level. And so our first level of our tree has 1, the second level of our tree has 2 nodes, the third has 4, and the fourth has 8 nodes. And if we add all of those up, it ends up being 2 to the 4 minus 1, or 16 minus 1. So the number of nodes that our tree can hold is related to a power of 2. If we have a completely filled binary tree, we can also identify what its height is, because we know that the number of nodes plus 1 is a power of 2. And so, for example, if we know that we have 15 nodes in our tree, 15 plus 1 is 16, and log base 2 of 16 is 4. So we know the height of our tree is 4. For a balanced tree, the height is approximately log base 2 of n. We know the height of a tree has to be an integer. When our tree isn't completely filled, sometimes we get fractional components because we don't have a completely filled tree. The height of a balanced binary tree with 1,000 nodes, for example, would be approximately 10, because a perfectly filled tree would have of level 10 would have 1,023 nodes in it. The height of a balanced binary tree that has 1,000,000 nodes in it is about 20, because the height of the balanced binary tree is about 6, because 1,000,000 is approximately 2 to the 20. And so that means that you can find any element in this tree with just 20 steps. That reflects that divide and conquer nature of a balanced binary tree. So if we want to look at an implementation for our binary tree, it's going to look very similar to our previous implementation of a tree structure in general. But what we're going to do is within the node, we're going to replace our child list. Instead of making it an array list, we're going to specifically say that we have a left and right child, both of which are nodes. We know that a node is a leaf node if both its left and right child are null. Here's an example. So in our binary tree class, you can see we have an interior class called the node class, like before. Our node class both holds data and it has children. And we've specified these children by name as the left and right variable within the node class, and they're both also references to nodes as you continue down this tree. When we create a binary tree, we're going to create it either with nothing by using a constructor that has no parameters, or if we want to create a binary tree that has something in it, we'll provide the root data, we'll provide the left tree and the right tree. In the constructor, we'll construct the root node. We'll assign the data of that root node to the data that was passed in by the constructor, and we'll assign the left and right subtree to the left and right subtree that were passed in as well. So with a structure like this, we can think about another kind of tree algorithm. We're trying to figure out what the height of a tree is. Now, if we wanted to figure out the size of a binary tree, we could use the same algorithm that we used previously in our tree. We could say it's 1 plus the size of our left tree and the size of our right tree. That would give us the total number of nodes within our tree. But that's not what we're asking right here. What we're asking here is what is the height of our tree? And the height of our tree, we know, is the maximum length of a path from the root to a child. So we can figure that out recursively by saying that the height of any given tree is 1 for the node that you're currently at, plus recursively asking what is the maximum of the height of our left tree and our right tree. Our left and our right tree have different heights on their own, and we're not going to sum them. We're just going to say which one is longest, and we're going to add 1 to it and return that as being the height of our tree. So the implementation of that looks similar to what we had for the size method. Again, we're going to implement the height method both in the binary tree class, and in the binary tree class, when we ask for the height, we're going to return the height from our root node. That, the bottom method, is not a recursive call. In the top example, though, we see that we're going to implement within our node class, within our binary tree class, a helper method also called height. This one is private, and so it can only be called from methods within the binary tree class, for example, the public height method. And our height method, the private one, is going to be the recursive one. It's going to take in a node as a parameter, and that's what makes it different from the public one. And if that node is null, it will return 0. And if it's not null, it's going to return 1 plus the max of the height of the left and right tree. And so our top method is recursive, and it's following that structure of returning 1 plus the max of the left and the right as we go on. As a recursive method, it meets the 2 qualities that we need for a recursive method to have. It has a base case. That base case is when n equals null. And it has a recursive case that's making the problem smaller. It's asking what the height is on the left tree and the right tree, and the left and right tree are necessarily 1 shorter than the current tree that you're at. All right, so that's the way that we implement the binary tree and the way that we reason about it. So let's ask some questions and do a little assessment to see if we're following along. Thank you.